Our next speaker is Josh Wrigley, who will tell us about eliminating imaginaries and adding structure. How does the geometric completion fit in?
Thank you very much. Thank you to the organisers for having me here. It's really nice to have a conference on such a specific and important topic, and I've really been enjoying it so far. So yes, my talk has quite a long title, which just discussing has some poetic connotations. But really, this talk is supposed to fill a gap in, because my supervisor quite likes announcing work before I started working on it. So this is Olivia Caramella. So this is to sort of fill in a gap in between some of the stuff I've already done and some of the stuff she says I'm going to do. So this fits into the wider field of completions of doctrines. And generally speaking, you look at the literature, there sort of seems to be two different kinds of completions you can consider for a doctrine. So when I say doctrine, I just mean a functor into preorders. So we've got some completions of doctrines where we add some nice structure to the fibers of our doctrine. So we've already seen one with the existential completion. But Dion Coman has a paper where she talks about this canonical extension of a coherent type of doctrine. And then we've got other kinds of completions where we change what we index and what's going on with the indexing category. So I'm going to be talking a bit about Schoffer's stratification work and these exactness type completions. So I know there's more people that need to be mentioned in that last slide than just Nilin, Strali, Mackay. Loads of people have worked in the last section. So to give an overview of what I'm going to talk about, I'm going to review this geometric completion. So we've seen how to complete to existential logic. I'm going to review how we can complete to geometric logic. And then from that, I'm going to describe some infinitary exactness style completions, generalizing, well, first of all, exact completions, the doctrines, but also some of the work done by Ross Street and Mike Schulman. And then finally, I'm going to sort of look at how this all fits within a relative Grothendieck-Topos framework and how we can understand completions of doctrines in that way. So let's begin with the geometric completion. So what do I mean by a geometric doctrine? It should be a coherent doctrine, which means I've got the structure to describe, well, it should be a regular doctrine in that it has a structure to describe regular logic, so I need left adjoint satisfying Frobenius and Beck-Chevalley, but I also want to have all of the structure of geometric logic, so I need all of my fibers to be frames. So far this is only over a Cartesian category. We're going to remove that assumption later.
Cartesian means finite problem.
No, finite limits. So yes, for this presentation, when I say primary, I mean full primary, and when I say existential, I mean full existential. Yes, all finite limits. Okay, and so just with this stuff we've already seen so far today, it's quite easy to construct what I would call the free geometric completion. So if we've got a full primary doctrine and a doctrine morphism to a geometric doctrine, then first of all we can take the existential completion, and this extends it to regular logic, and then we can apply the pointwise for each one, so we can freely apply joins to all of our fibers, and this gives us a free geometric completion satisfying the universal property that we would desire. But there are a few issues. It's not idempotent, for one thing, and generally we quite like completions to be idempotent.
Why?
Sorry?
Why?
I like completions to be idempotent. On top of that, if we wanted to, say, consider that that was the free geometric completion for primary doctrines, so it satisfies the universal property with respect to morphisms of primary doctrines. we wanted to do the same for coherent doctrines or these other intermediate doctrines. We would actually, in order to get the correct universal property, we would end up with a different notion of a free geometric completion. So the idea behind the full geometric completion is to take care of all of these different levels and take care of this idempotency. And so this is a free geometric completion in the sense that we're just free generating with respect to some generators, but we haven't added any relations. So we need to add relations into our framework in order to get idempotency and this multi-layered completion. And for geometric logic, at least, this looks like adding Grothendieck topologies into the mix. So let's add some Grothendieck topologies into the mix. This is the definition of the doctrinal site, which is this quadruple, where the first two components are a site, we've got our base category and a topology on our category. And then we have a doctrine over our base category, and we are going to apply with a Grothendieck topology on here. This C times P is my notation for the Grothendieck construction. So we've got a Grothendieck topology on the Grothendieck construction. And we need some properties on that Grothendieck topology. We need it to contain the Giraud topology, which is the same as saying that the projection from the Grothendieck construction to the base category has the cover lifting property. That is to say, it's a comorphism of sites. So what's going on here is that we have our base categories representing some sort of base algebraic structure. The Grothendieck topology is adding in any extra logical structure that we've got going on in the base. And then this Grothendieck topology K is then adding in any of the extra logical rules that are happening in our doctrine. So, and then a morphism of doctrinal sites is going to be a morphism of doctrines in the usual sense, where we've got just any old functor between our base categories and a natural transformation between our doctrines, such that this functor is a morphism of sites, which means that it doesn't necessarily have to preserve finite limits, because those finite limits might not exist, but it has to preserve them relatively with respect to the topology, and it has to also send covers to covers. And we also require this F times A, this morphism of vibrations induced by natural transformation, to also be a morphism of sites and to also relatively preserve finite limits and preserve covers. So let's just do a quick sanity check that this is one of the correct ways that we should be working. We have full and faithful embeddings of primary doctrines into doctrinal sites. This is given by just taking the trivial topology on everything. We can embed existential doctrines into doctrinal sites as well by taking this topology where we're generating the topology by these covers given by the existential quantification. And we can also embed coherent doctrines into doctrinal sites by doing the same thing where we're taking the covering data from the existential quantification and also by the join, the finite join between the two propositions. So this seems to be like a fairly good notion, and of course you can see where this is going. We've added in regular logic and coherent logic, so we want to do geometric logic as well. Yes?
You said you put the coherent topology on the total category of the vibration?
So this isn't the coherent topology in the usual sense that you've got a coherent category.
Because it's not necessarily coherent.
It's not,
but it's something resembling that.
Exactly. Yeah. And so for geometric doctrine, we're going to do the same sort of thing. Notice here that we're removing the requirement that C is Cartesian. So a geometric doctrine over this is, over a site Cj is going to be a functor taking values in frames and open frame homomorphisms. That is, we have left adjoints to our frame homomorphisms that satisfy Frobenius. And we also need an extra condition. We would, if we are over a Cartesian site, we can just take the Beck-Chevalier condition. But we need something else, even in the case when we don't have finite limits in our base category. So these are actually equivalent conditions, these extra conditions we want to put on a geometric doctrine. The first one is that it's an internal locale, it's a locale in the internal language of our sheaf topos. And then the second equivalent condition is that we want this assignment of SIDs to define the Grothendieck topology. So this is just generalizing the not quite coherent topology we saw from earlier. And you can see that this assignment of SIDs satisfies the maximality condition to be a Grothendieck topology. It satisfies the transitivity proposition, but it doesn't always satisfy the stability condition. And Frobenius reciprocity is giving us the stability condition along maps in the same fibre, but for maps between fibres, that's where we would need the Beck-Chevalier condition, but in this case we don't have it. So we'll just impose that as an assumption. So this is in Olivier Caramello's preprint fibre existential sites. This is called the relative Beck-Chevalier condition, and whenever we have pullbacks in our base category, this is equivalent to the Beck-Chevalier condition. Okay, and with this definition of geometric doctrines, we're able to construct, well, I haven't talked about the two-dimensional structure, but there's an obvious two-dimensional structure we would want to put on all of this. And we can construct to a junction between geometric doctrines and doctrinal sites such that this completion is now highly potent, as well as being universal. Okay, so how would we actually compute the geometric completion? Well, we know from earlier that the projection from a Grothendieck construction to its base category is a comorphism of sites, which means it induces a geometric morphism between sheaf toposis. And whenever we have an object in our codomain topos, then we can look at the lattice of sub-objects in the domain topos of the image under the inverse image functor. This is a frame, and indeed, if we just computed it for all objects and considered the arrows given by pullbacks, this ends up being a geometric doctrine over a Cartesian category. And we can compute the geometric completion of an arbitrary doctrinal site by just precomposing with the canonical functor of the category into its sheaf topos. So we have the geometric completion of a doctrinal site, and this includes in particular the free geometric completion from earlier. And whenever we come across a new completion of doctrines, the obvious question is, what does its exact completion look like? And the question then is, which one? So I use this term elimination of imaginaries, which is sort of poetic terminology taken from model theory, where Shelar studied this elimination of imaginaries process, which is this idea that if you've got a definable partial equivalence relation, you want to have a sort that interprets that partial equivalence relation. And being categorical logicians, we would expect there to be some sort of categorical version of it, and indeed Mackay observed that his pre-topos completion that he studied with Mackay and Reyes is this categorical formulation of what it means to be elimination of imaginaries for a coherent theory. And there's this huge different class of what it means to be an exact completion, and we're going to be following this sort of stratified approach, I believe initiated by a paper by Ross Street, but as mentioned, Mike Schumann has also studied it as well. So I'm just going to go through and sort of talk about what these different stratified exact completions look like for a geometric doctrine. So if we've got a geometric doctrine over a Cartesian base category, we can define what I would call the syntactic category. where the objects are pairs of predicates of our doctrine, and the arrows between two predicates are going to be provably functional relations in the internal language of our doctrine. This is the syntactic category in the sense of imaginaries in the particular case where this is a doctrine coming from a geometric theory. We also have what we might want to call its exact completion, where, okay, so yeah, I should also mention here that we're doing this over a Cartesian-based category, so everything makes sense, but once again we're going to remove this assumption later. So we can define its category of partial equivalence relations, which would look like the tripos to topos construction. So we take our object to be definable partial equivalence relations in the internal language, and we define our maps between two partial equivalence relations to be those relations which describe provably functional relations between them. So this is all happening in the internal language of the doctrine. But because we're in geometric logic, we can go beyond this. We can...
So what you're writing is equality that's not really equality. It's just
no, this is equality in the internal language.
But I mean, F is a binary relation, right? So it's this
yes.
is syntactic sugar.
This is syntactic sugar, yeah. So it's when we say this, like implies, it means that we are less than the image of the top element underneath the left adjoint of F times the identity.
Yeah. That's not what I meant, but I think.
I think the X is the equation.
I mean, your writing is as if F was a morphism, but F is not a morphism.
Exactly. Yeah. No, so when I write F of X equals Y, this is just sugar for X and Y in the graph.
Exactly.
Sorry. Okay, and then when we take any infinite cardinal, we can also consider families of partial equivalence relations. So I think, yes, I've written at most length kappa, but really that should be length less than kappa. But anyway, we've got these tuples of partial equivalence relations, and then we want to define provably functional formulas between these. And so we can define them in an analogous way, where the first condition is saying that our provably functional formula. Yeah, so what we do to define a function, we have to split it up in between the indexing on each partial equivalence relation. And so then each of these has to be provably functional in the sense that it's well defined for the partial equivalence relations, it respects the partial equivalence relations, it's functional, but we need an axiom which says, in the previous case we needed an axiom which said that it was total, but here, because we've got families of partial equivalence relations, this is actually, we say that it's total over all of the possible provably functional, over all of the partial equivalence relations in the codomain. So this is why we need geometric logic in order to do this for arbitrary infinite cardinals, because we would need to put a massive join in that bottom equation in order to describe totality. So now we've got this sort of stratified version of what's going on with all of these categories of partial equivalence relations. What are they actually describing? So the infinite category of partial equivalence relations is just the infinity pre-topos completion of the syntactic category of our geometric doctrine.
And that's for unbounded kappa.
That's for unbounded kappa, yes, so we take kappa to be as big as we can. And this is actually equivalent to the topos of internal sheaves. So whenever you've got an internal locale, you can perform its sheaf construction, and we actually get back this infinity partial equivalence relation construction, and we can break down explicitly a site for this Grothendieck topos. And so now that we've seen what happens in the case when we've got a Cartesian-based category, we can use this topos-theoretic perspective to start thinking about what happens when we remove that assumption. Yes? Oh, sorry.
I said 3 minutes.
3 minutes, okay, perfect. We can start wondering what would happen when we remove the Cartesian baseness assumption. And so we end up with this large table where we've got these stratified exactness properties. So we've got a level describing which kappa you take, and then each of these we can sort of. This isn't direct one-to-one equivalence. It's not saying that if we take the full subcategory of sub-representables, that is sub-objects of a representable in this topos, then it always gives the syntactic category. It's saying that it does in the case when we have the Cartesian baseness assumption, because these categories here won't have the finite limit structure that we would want them to have, because that's actually coming from the indexing category that you're starting off with. So these categories here that we're taking are these sort of generalized exactness completions, in that we're adding the objects interpreting partial equivalence relations. So they have all of the exactness properties you would want, but we haven't started from something with finite limits, and so we don't end up with something with finite limits. But what is interesting is that when you take the whole topos, which is to say you take infinite families of partial equivalence relations of a geometric completion, then you do end up with something with finite limits, and you do end up with a Grothendieck topos. Okay. And so very quickly, my last remaining time, I want to relate this to other recent work about what happens when we don't have this structure in the base category and we want to add, say, finite limits, but we don't want to include any of that data coming from the fibers in the doctrine. We're not going to include properties about the internal predicates. So this is based off some recent work which I'm very grateful to Rosaline to having informed me about Chart's preprint, which is this idea that if you've got a primary doctrine but where your category underneath has only weak finite limits, then you'd want to consider its strictification, its extension to this free finite limit completion in order to construct its exact completion. And we can sort of consider what this might look like in the geometric case, because whenever we have a base category and a Grothendieck topology on that category, then we can find another topology on its finite limit completion such that there's an equivalence of toposes. And so we could generalize strictification in the geometric setting by taking this concept of where we take the canonical functor, the finite limit completion of C, into its sheaf topos across this equivalence, and then we apply the geometric completion to get a sort of geometric strictification of an arbitrary doctrine set. Okay, I believe I'm out of time, so I'll finish with some references. Thank you very much.
Why do you start from pre-orders without into pre-orders, without pre-orders?
Why instead of post-ups?
Yeah. Why examples?
Because when you geometrically complete, it automatically becomes a post-up.
Just for generality.
Yeah, just for generality. Yeah.
You have a question?
I have a question. So, you have these kappa families of partial equivalence relations. I thought about a similar construction, but shouldn't it be heterogeneous equivalence relations? Do you know what I mean?
What do you mean by that?
I mean that you have binary relations between different carriers, and you have transitivity, like if something in this carrier is related to something in this carrier. with.
So the idea that I
Because I
had,
know that you can represent chief topos for the canonical topology in terms of heterogeneous equivalence relations on the generator somehow. Like similar to if you have a manifold patching together from small pieces that you glue things from different parts. But
Yeah.
maybe you're doing something else.
it sounds like that would be possible to, it's obviously possible to define it. I'm not sure if that would give you the same result out.
Yeah, maybe. Yeah.
Because so the idea that I had in my head is that once you have all of the exactness conditions of the Grothendieck-Topos, then really we are taking like a co-product of the sorts, and then considering some sub-object of this, and then taking something covered down here. And so then this E is a collection of partial equivalence relations. So
No, but now this looks like you're gluing together pieces because now you can identify things from different parts of your co-product. That looks like a heterogeneous.
yeah. I mean, okay. I have to think about like if you get it exactly the same. But yeah, no, that's interesting. It potentially has like an equivalence description.
Yeah.
Yeah.
And so in your this hypercoded completion, does the base topos change?
The base topos stays the same.
Okay.
So the way that you define, yeah, I mean it is literally just.
So the CJ stays the same, and the
So this
just
topos stays the same, and you take this geometric morphism localic, and you take the internal locale to find like localic geometric morphism, which is the same as going from C into here, and then considering sub-objects and things out of the first image.
Any more questions?
Can you say a bit about the idea behind having these different levels? So, like, how does it actually relate the exact completion to having, say, two levels of? Is it two levels or one level? I'm not sure. It's not.
Okay, so yeah,
level one, but it's two equivalence relations. Is it correct?
so the exact completion in of like adding a object to carry any partial equivalence relation is just for one level.
Oh, I see. So
Yeah.
it's adding one. And so what would happen for level two? Let's say.
I think it only makes sense to talk about it for limit
Oh, I see.
ordinals. If you had two, it sounds like you're able to make a binary co-product, and so you can make infinitely many co-products.
Why? Because I mean the question. So when you want to relate it to heterogeneous relations, it's not just arbitrary, right? There's a bound on how many things you can somehow compare in one relation. Right?
Yes. Yeah.
So
Okay. Do you have another question?
No, I just asked it after.
Okay, so maybe I should stop here. We can
Yeah.
continue discussing. Let's thank the speaker again.